So let us discuss this example of metric. See, first of all, we will try to understand the definition of D, and after that we will prove that it is a metric. Okay. So see, what is X here? X is a set of all real sequences. Okay. X is a set of all real sequences. Sequences, that means elements will be like this. X is equal to xn, having entries x1, x2, x3. In this way we have a sequence. Suppose if you consider y, so yn is equal to y1, y2, y3. All these are sequences, okay, which are members of X. See, they have defined D in this way. See, if X and Y are same, that means x1 is equal to y1, x2 is equal to y2, x3 is equal to y3. If all are equal, then we can say x is equal to y, and in that case value of D of xy is 0. But see, there are possibilities that xi is not equal to y for some, that means x is not equal to y. Okay, so that means suppose we have a sequence. Okay, for example, I will take this, suppose consider one sequence that is 2, 4, 6, 8, 10, 12. Suppose this is sequence x, and y is equal to 2, 4, 6, 10, 25, 36. You are getting, suppose this is first sequence and this is second sequence. Tell me, these two sequences are same? No. Since few entries are same, I can understand, but remaining entries are not same now. So that's why these two sequences are not same. X is not equal to y. So in that case, distance between x and y, D of xy, will be like this. See, 1 upon minimum of, okay, xi is not equal to yi. See, tell me, x1 is equal to y1? Yes. x2 is equal to y2? Yes. x3 is equal to y3? Yes. x4 is equal to y4? No. Okay, that means at fourth position, okay, at fourth position, we get our first inequality. So that's why minimum of the inequality, that means here 4. Getting here, you can say x5 is not equal to y5, x6 is not equal to y6. That is also okay. But first inequality we get at fourth position. So that's why its minimum is 4. So 1 by 4. So D of xy is 1 by 4. In this way, they have defined a function D. So now our task is to prove D is a metric on X. Okay, so you know that how to prove a metric. So that means we have to simply prove it satisfies 4 conditions. So let us start to discuss all those conditions one by one. Okay, just a minute. I will remove this part, and after that we'll go for all conditions. Okay, just a minute. You remember the first condition. First condition is non-negativity. That means if I take two sequences, okay, first, for if I take two sequences, x is equal to x1, x2, x3 and so on. This is the first sequence, and y is equal to y1, y2, y3. This is the second sequence. Okay, so we have two sequences. Clearly I can mention minimum of I, xi is not equal to yi is greater than 0. Okay, see, I denotes position, first position, second position, third position. That means all these are natural numbers, they cannot be 0. So that's why whatever, okay, all numbers are natural numbers. So that's why minimum of them is also natural number. So it will be 101% greater than 0, right? Greater than 0 means positive. If I take reciprocal of any positive, then also we will have a positive number. So that's why I can write 1 upon minimum of I x such that xi is not equal to yi, that is also greater than 0. This is positive, so its reciprocal is also positive. But see, this is definition of D. This is definition of D. So that means this one is positive and this one is 0. That means we never get a negative. Okay, value of D has a two different definitions, right? First definition says its value 0. Second definition gives positive number. That means there are no chances of getting negative number. So that's why I can write D of xy is always greater than or equal to 0 for all xy belongs to X. I should mention by definition. We have used definition. So by definition, right? So that's why in this way we proved first property of D. After that we will try to discuss second property, but before that make a screenshot of it, and after that we'll go for second property. Okay, Okay, so let us discuss second condition. Okay, so what is second condition? Second condition, that means d of xy is equal to, second condition is d of xy is equal to 0 if and only if x is equal to y, right? But see, d has two distinct definitions, right? So we have a separate technique if the function has a two distinct definitions, and in our previous 2-3 videos we have already solved examples of that type, right? So let us start to do. So here we will discuss two cases, x is equal to y, and after that second case is obviously x is not equal to y. So let us start. So here I am considering for x, y belongs to x. So first case is if x is equal to y, implies, see, definition says if x is equal to y, distance between x and y is 0, right? Let us try for second condition, x is not equal to y. See what will happen if x is not equal to y, distance between x and y. If x is not equal to y, we should go for second condition, second definition, right? So 1 upon minimum of I such that xi is not equal to yi, right? So d of xy is equal to this one. So 1 upon minimum, see, it is a natural number, 101% it gives a natural number, and 1 upon natural number, that means we will have positive number, so it is greater than 0. It means d of xy is greater than 0, that means d of xy is not equal to 0. So if x is equal to y, then we get d of xy 0, but if x is not equal to y, we are getting d of xy not equal to 0. That means we value of d of xy is 0 only if x is equal to y. Getting it? So therefore from these two cases we conclude d of xy is equal to 0 if and only if x is equal to y. So in this way we proved second property. Also we will go for third property, but before that make a screenshot of it. Okay, so let us discuss third condition. Third condition is d of xy is equal to d of yx, right? But see, function has two distinct definitions. So what will I do? I will discuss two cases here. First case is x is equal to y. Second case is x is not equal to y, right? So see, so third condition. So see, for xy belongs to x, any arbitrary xy I am choosing. Case 1 is if x is equal to y. See what will happen if x is equal to y, definition says d of xy is equal to 0. Okay, so by definition d of xy is equal to 0, and obviously d of yx is also equal to 0. Since x is equal to y, then y is also equal to x, both of them are same, so obviously value is 0. So d of xy is 0, d of y is 0, so that means both of them are same. Getting my point? So d of xy is same as d of yx. Okay, so in this case we have proved third property. Okay, but let us go for the second case also. What is the second case? Second case is obviously x is not equal to y. See, if x is not equal to y, that means we have to follow the second definition, right? So therefore d of xy, second definition says its value is 1 upon minimum of I such that xi is not equal to yi. Tell me, a is not equal to b, right? Is same as b is not equal to a. Agree with me? So here what can I write? 1 upon minimum of I, which is same as yi is not equal to xi. Xi is not equal to yi is nothing but y is not equal to xi. What is the purpose behind it? We have to prove symmetry, no? So that's why we want to interchange them. That's why I did this. So this is equal to, this is nothing but d of y, since y appears first. So that's why I took y first. So d of xy is equal to d of yx. Here also d of xy is equal to d of yx. That means in both cases we get. In short, I will mention here simply. So see, from above two cases, what we conclude, d of xy is same as d of yx, and for all xy belongs to x. So symmetry we proved. So therefore third property is also we have done here. Okay, so only last property we have to prove, but before that make a screenshot of it, and after that we will go for last property also. Okay, please. Okay, so let us discuss fourth condition, right? So for fourth condition, it is known as actually triangle inequality. How you remember now that triangle inequality d of xz is less than or equal to d of xy plus d of yz, right? How many elements are required here? 3 elements. I have already taken x, y and z. So as I already told you in our previous videos that if we have, okay, if the given function has two distinct definitions, then we have to discuss several cases. Okay, I think 5 cases we have already discussed for in 2 or 3 examples. Okay, so let us do the same. So here also I am going to discuss few cases. Case number 1. Can you tell me what is case number 1? So case number 1 is all are equal. X is equal to y, which is equal to z. See what will happen in that case. Dxz is 0, since definition says if elements are equal, value is 0. So dxz, dxy is also 0, and dyz, that is also 0. Getting now, since elements are same now, so that's why distance is 0. So therefore I can write dxz is equal to dxy plus dyz. Since dxz is 0, left hand side is 0, and if you think about right hand side, so both of them are 0. If you add zeros, we will have 0, right? So left hand side is 0, right hand side is 0. So here we get a equality. Okay, yeah, we get a equality. Let us go for the second case, case number 2. Yeah, you can also guess. Case number 2 is x is equal to y, which is not equal to z. That means what we do, we consider first 2 elements are same and the last one is different. Okay, so in this case what will happen, d of xy is 0. Agree with me? Since elements are same, so that's why d of xy 0. And d of xz is equal to d of yz. Agree with me? Since x is equal to y, no, so you can replace x by y. One thing I'm going to do, 0 plus dyz. Actually, it doesn't matter since we are adding 0. If you add 0 in any number, you will have a same number. But 0 is nothing but d of xy. So this is equal to d of xy plus d of yz. D of xy plus, since d of xy is 0, right? What is our left hand side? D of xz. So d of xz is equal to d of xy plus d of yz. That means again same thing we have got, right? In first case also we have got equality, and in second case also we have got equality. Let us discuss the third case. Tell me what is our third case, please. Yeah, try to think. What is our third case? Third case is obviously, yeah, what we have considered, first 2 are equal, last one is different. So now what will I do? I will consider last 2 elements are same and the first one is different. So that means here I will consider x is not equal to y, which is equal to z. So therefore, see, therefore d of yz is equal to 0. D of yz is equal to 0 because these 2 elements are same, and if elements are same, value of d is 0, correct? And d of xz is equal to d of, what I should write, xy. Since z is same as y, so that's why I could replace z by y. Again, I'm going to use the same technique. I'm going to add 0 there. So d of xy plus 0. See, if you add 0, you will have same, but 0 is nothing but d of yz. So this is d of xy plus d of yz. Okay, so what is our left hand side? D of xz, and what we are getting, d of xz is equal to d of xy plus d of yz. So here we get equality, here we get equality, and in this case also we get equality. Okay, let us go for next case. What is our next case? Case number 4. What is our case number 4? Yeah, see, all are same. First 2 are same, last 2 are same. Now I will consider first and last are same, middle one is different. That means x is equal to z, which is not equal to y. So therefore, d of xz is 0 in this case. Agree with me, since x and z are same. And d of xy is greater than 0 since both are different. And d of yz, that is also greater than 0 since both of y and z are distinct. So see, this is positive, this is positive. If you add 2 positive numbers, again we will have a positive number. So therefore 0 less than d of xy plus d of yz. Both of them are positive. So if you add, again it is positive. But 0 is nothing but d of xz. So therefore, d of xz is less than d of xy plus d of yz. Agree with me? So that means here we get inequality. Okay, very important thing. In first case we get equality, second case we get equality, third case we get equality, but in last case we get strictly inequality. Only one case is remaining now, that is all three elements are different, distinct. Okay, so let us go for the last case, but before that make a screenshot of it, and after that we'll go for the last case. One more thing. Okay, please look this problem carefully because I am going to rough it. Okay, the last case is little bit lengthy, so I will make the entire blackboard clean and then we'll go for a last case. Please make a screenshot of this board. Okay, so let us discuss the last case. For last case we require three elements x, y, z. Yeah, so x, y, z. All three are distinct. We have already assumed. Getting? So see, these three sequences are not same. X is different, y is different, z is different. So obviously few terms are different, 100%. So what can I write here? So I can choose here. Let what I'm going to do. L is equal to minimum of I such that xi is not equal to zi. You are getting the point. X and z are distinct, different sequences. So elements are different. So the minimum of xi is not equal to z, that means L. That is, it means actually x1 is equal to z1, right? x2 is equal to z2. It is true up to xl minus 1 is equal to zl minus 1, but xl is not equal to zl, right? Since it is a minimum where we get an inequality. So at L position we get inequality. Similarly, I will consider let m is equal to minimum of I such that xi is not equal to yi. That is what can I write? That is x1 is equal to y1, correct? x2 is equal to y2, and it is true up to x m minus 1 is equal to y m minus 1, but at nth position we get inequality, right? Okay, similarly, see, for x and z, for x and y, and obviously last one is for y and z. So let n is equal to minimum of I where yi is not equal to zi. That is, can you tell me that is what is it, what it means? Can you tell me? Yes, obviously it is y1 is equal to z1 now, y2 is equal to z2 now, and it is true up to y n minus 1 is equal to z n minus 1, but yn is not equal to zn. Getting the point? Okay, so after that, what will I do? I will assume, I'm going to assume, I'm assuming L is less than m and L is less than n. See what will happen if L is less than m and L is less than n, implies, see, here is m, so L is less than m, so L is less than m, that means it can be m minus 1, can be m minus 2, can be 2, can be 1, like that. Understood na? So if L is less than m, so for less than m we have equality, so therefore I can write xl is equal to yl. Getting my point? For m if L is less than m, we have a equality, so that's why I could write xl is equal to yl. Here L is less than n. This is a case of n, right? L is less than n, that means it can be n minus 1, can be n minus 2. But see, if it is less than n, we have an equality of y and z, so therefore I can write yl is equal to zl. Getting my point? So see, xl is equal to yl is equal to zl. It means xl is equal to zl. Agree with me? A is equal to B, B is equal to C. So A is equal to C, but we get a contradiction because already we have C written here, XL is not equal to ZL. Okay, so I write we get contradiction. Okay, we get contradiction. So therefore, what we have assumed is wrong. Therefore, I will simply mention our assumption is wrong. Our assumption is wrong. So that means, what was our assumption? Yeah, our assumption was L is less than M and L is less than N. So that is wrong. So therefore, L is greater than or equal to M, or L is greater than or equal to N, right? Okay. So if I take reciprocal, inequality will get changed. So therefore, if I take reciprocal, we will have 1 upon L less than or equal to 1 upon N, or here also 1 upon L less than or equal to 1 upon N. Agree with me? So that means 1 upon L less than or equal to 1 upon M, plus if you add 1 by N, you will have this thing. Agree with me? It is less than 1 by M, it is less than 1 by N. If you add, then also it is less than 1 by M plus 1 by N. That is 1 by L means what? L means minimum of this one. So I should write 1 by minimum of I, where xi is not equal to zi. We don't have much space. I am writing here less than or equal to. M means what? M means M. Yes, minimum of. Yeah, it is minimum of I such that xi is not equal to yi plus n. 1 by n means what? 1 upon minimum of, as you can see the definition of n, I, where y is not equal to zi. Yi is not equal to zi. That is, this is nothing but d of xz. This is given definition, no? Less than or equal to d of xy plus d of yz, right? So that means in all cases, therefore, from all cases I will simply mention from all cases, what can I write from all cases? In all cases we get either equality or inequality. Okay, so less than or equal to d of xy plus d of yz, and this is true for all x, y, z belongs to x. So in this way we have proved that D satisfies the last property also. First four conditions, sorry, so first three conditions already we have proved. So we have proved D satisfies last condition also. Therefore we can declare, therefore D is metric on X. Okay, so in this way we completed the example. Simply make a screenshot of it, and after that we will stop. Thank you. Bye bye.